Okay, so for the last video, we're going to talk about sort of understanding the connection between a function and its derivative. So a function, I just mean like y equals. Its derivative, I just mean the dy dx thing. And then we're going to look at optimization as well. So let's just close that one up there and let's just have a think about what's going on here. So imagine this is my graph, and then I wanted to actually draw what the what the gradient function looks like. So think about lots of tangents here. And what can you say is true in the first interval? Well, the gradient is positive, but it's getting less and less positive, isn't it? That's how the gradient's changing. So I'll start off quite positive. Maybe the gradient there could be like 8. And then what could that be? Maybe 3. Then maybe 1. And hopefully you can see there that I could generate that section. If I wanted to draw the gradient at each point, it would look like this. Notice how I've lined them up deliberately as well, because the gradient depends on the x value. What happens to the gradient here? You should know this one. It goes to 0 because it's a stationary point. And then after that, there's a negative gradient. It's negative and it seems to be getting more negative. So that's why it's going like this. And then there's a point here where it's getting less. So it's negative, but it's getting less negative. It's negative, but it's getting less negative. Negative, but less negative. So we've got a journey that looks a bit like this. And it gets to another one of these stationary points. Well, we know that's when dy dx equals 0. And finally, it's negative and more negative, more negative, more negative. So we get something like this at the end. Much easier to do this task if you break it down into sections and you try and narrate what's happening each time. So here's another one. Let's have a look. This is the original graph, and we're going to sketch its gradient. So what's happening to the gradient? It's negative, 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 but it's getting less negative each time. It's only really perhaps noticeable around here that it's getting less negative. So the gradient's negative, but eventually it's not negative. It's just going to be 0 at some point. Okay? Afterwards, it goes from 0 to positive to positive to more positive to more positive to more positive. So the gradient looks a bit like that, perhaps. And why is this useful? Well, this is useful because we can link it back to our drawing of graphs. You might remember from chapter 4, what we could do is we were sketching graphs. So what we're doing here, so we're by first finding stationary points. So stationary points are when dy dx equals 0, and we can find x values, we can find the corresponding y values by plugging them back in here. Okay. These are turning points of this graph. We might also want to look at some extreme values because it's quite hard to draw this thing here. So what happens for very big values of x? Well, for very big values of x, y gets very big. For very negative values of x, y gets very negative. Also, do we have any vertical asymptotes? Well, when we have 0, we'll be doing 1 divided by 0, and we're not allowed to do that. So if we put this all together, we can sort of come up with a bit of a graph. It's like a reciprocal graph. We know some points here where we've got some turning points. We know what happens with the tails as well. And we know that there is an asymptote down the middle. And if you sort of piece that together, you can end up drawing some fairly complex things. But please don't worry too much if this one seems a bit unusual to you. It is quite an unusual one to be asked to draw. Okay, so we're going to have a look now at the last part, which is optimization. Where do we start? Here. So imagine we have some problems now. Like, let's go back to the train track and trying to find when the train was furthest away, or how we could make the area of a triangle as big as possible. These are optimization problems, and this is really the most useful part of differentiation. So we can answer questions like this one here. we have 15 meters of fencing. We want to make a bear pen, and this is the shape. So something about a semicircle and a rectangle. And we want to make the area as big as possible. I mean, if you have limited resources and you want to build an area, you try and maximize it, right? That seems pretty intuitive. If you want to do that, what should your X and your Y be? Well, you can actually answer these kind of questions, and we're going to do that now. So up to now, we've mostly been doing questions with dy dx. And what this means is it shows you how does the y value change as the x value changes. Like, let's go back to the starting point. How does the x value change? Sorry, how does the y value change as the x value changes? That's where we began. But that's pretty sort of abstract, and it's about graphs and things like that. We're going to do it for like real things now. So imagine we have a question like this. We have some container filling at this speed here. How could we represent this? How could we draw this? Because this is not so apparent that it's about y and it's about x. The rate at which something changes with respect to something. Well, what's changing here? Some sort of volume is changing, isn't it? With respect to what? Well, with respect to time, for example. So for sort of a real life idea like this, you might use dv dt. This means, how is the volume changing as time goes on? Well, as time goes on by 1 second, the volume's changing by positive 20. In other words, there's 20 more each second. Okay. And I'll just show you this one here. This isn't actually in the book, but I think this is just a nice example of optimization using one variable. So it says, imagine if you have a piece of paper that's 30 centimeters by 30 centimeters. I know it's a bit unusual having a square piece of paper, but just go with it. And you want to you're going to fold some of the sides in. Okay, you're going to fold some of the sides in because you're going to make a box. Okay, from one piece of paper. And I want to make a box with the greatest, not the greatest height, the greatest volume. So how could I use one piece of paper in the best possible way so that I could contain the most stuff? Well, if this is 30, this distance here, and this becomes the height and the height, what you do is you have a square in the middle. That is 30 minus 2h, and it's squared because it's a square. Okay. And the height will be h. So this is the kind of shape that you can make. Right. So what we could do is we could actually work out the volume. This is, this is quite a common shape. We know how to deal with this. Okay. It's just a rectangular prism. So I just take the front. Multiply it by the depth. Okay. And the height here as well. And I could come up with this equation, this formula, in fact, for V equals. Now, there must be like a perfect height. There must be a perfect height for this box, because if you make it too big, then you'll get a really, really small square at the bottom, but it will just have a really, really big height. Okay. But if you make it too small, then you'll just have a box with like tiny, 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 it would have a very small height on it. You won't be able to fit much in it. So how do we find the perfect amount? Well, if we differentiate it, we can find, how does the volume change as you change h? H being the thing you choose for how high up you want it to go, the height on your box. Well, we differentiate it and we end up with something like this. Now, this tells you how volume changes with height. It's a quadratic. So what will happen is when you draw this, there will be some values. Hang on, let me just check this one a second. Minus 4h squared. Yeah, there'll be some values here. So what was I talking about? There'll be some values here that would give you a very, very large volume, okay, and some that would give you a very, very small volume. If we differentiate it, though, we're kind of interested in the turning volume, okay, the turning volume. So let's just oversimplify it. Let's do something like this. The maximum volume would be at some point like this, where the stationary, it would be a stationary point where dy dx is equal to 0. Or in this question, dv dh is equal to 0. And if you do that, if you set this thing equal to 0, you will find some values for h. Okay? If you set it equal to 0 and find the maximum, you will find the amount for h that makes this box as big as possible. And that's an optimization problem. So let's have a look at a question. Now, in some ways, this is easier, but in some ways, this question is more difficult. So what you'll normally get with these questions is you'll get two different variables, x and y. So that's what makes this a bit more complicated than the one that you've just looked at. Now, you'll have to do something often with area and something with volume. You'll normally get two equations, and you're going to have to use them together simultaneously. So let's have a look at this. A large tank in the shape of a cuboid is to be made from 54 meters squared of sheet material. The tank has a horizontal base and no top. The height is x meters. Yeah. Two of the opposite vertical faces are squares. Yeah. Okay, so that's x squared and x squared. Show this thing here. Okay, so how on earth do we get started here? Well, first of all, you need to look at what you've got in the question. You've got something about area, and then you've got something about volume. So you need to make two equations, one about area and one about volume. You also notice that x is being used. So you need something about x in these here. Now, what else is going on? Well, y appears in the question, but it doesn't appear here. So in other words, you're going to make two equations and you're going to solve them simultaneously by using y. And that's why it doesn't appear in there at all. Let's have a look at, should we do a neat version of the question? No, let's just do the question. So let's make an area equation. So what's the area? Remember, there's no top to this thing. So there's an x squared and there's another x squared on the other side. So I'm going to say 2x squared. Let's do the front and the back. So this is xy, 2xy. Now it also has a base, and the base is also xy. So actually it's going to be 3xy. That's the area. Notice they gave you the actual value for the area. They said 54. So this is an equation I've made. Volume. Let's do volume now, because the question is all about volume. What's the volume? Well, the volume is just multiplying these things together. So I'm going to do, let's do x squared y. And it says v equals, so I kind of want v to stay there. I don't need to do anything with that. The trick now then is to solve these together. And I need to make the y disappear because it doesn't appear in either part. So we could take the a formula and we could do 54 minus 2x squared equals 3xy. You want y equals, so let's just divide that by 3x as well while we're at it. Hang on a second. Yeah, so divide that one there by 3x. Okay, if we do that, I'm going to get y equals 54 over 3 is 18. That's a very good sign. You always want to look ahead a little bit. So 18 over x. and breaking this up into two parts. Okay, and then this is going to be minus 2/3 x. And can you see it looks a little bit like that already, which is reassuring. So now I've done this part here, I'm going to substitute this one in to the other equation. That's over here. So v equals x squared multiplied by 18 over x minus 2/3 x. And you can see, whoops, didn't really mean to do it like that. You can see I'm going to get 18x minus 2/3 x cubed. Okay, which is what they want on the show that part. It's not the end of the world, by the way, if you don't get part A, because you can use the result in part A to answer part B now. Given that x can vary, in other words, x is a variable, we can sort of differentiate with it. Use differentiation to find the maximum or the minimum value of v. So that is v equals. Use differentiation. We're going to do dv dx, which is equal to 18 minus, don't forget to multiply, they'll cancel out when you multiply, minus 2x squared. Maximum or minimum? There is a maximum or minimum when dv over dx equals 0. So 0 equals 18 minus 2x squared. What are we going to get? We're going to get x equals plus or minus 3, aren't we? Okay, so 2x divide 9, yeah. Just one thing to be aware of, x is a dimension for a box, so x equals minus 3 is not valid. So we want x equals 3. The maximum or minimum value of v, well, this is just the x that makes the maximum or minimum happen. What actually is the value of v? You need to sub it in, okay? So sub into v equals. And if you do that, have we got, yeah, if we do that on this one here, so the y is gone, we're going to get our answer. In fact, this was an example, wasn't it? So that will be 54 from there. That will be 27 divided by 3 will be 9 minus 18. So 36 is what I get, okay? That the volume would be 36 meters cubed. Let's just double check. Yeah, 27, 9. Okay, so let's check the neat version. So what we do is we make a formula for the area, a formula for the volume, lots of clues, and you want to use the clues in the question. So you know that y is used to eliminate because y doesn't appear in this part here. We get v equals as required. Remember, it's a show that, so you need to show you're working out clearly. And then I found x equals 3. I found the value that made a turning point, and I put that in. I didn't show that it was a maximum or a minimum because it didn't ask me to do that. It just said use it to find the maximum or minimum value, and there was only one, so I just put that number in. So time for you to pause and have a go at the question on the board. Use the hints as well to help you. Okay, so the length of the edges, so the volume, the rectangular. So you need to use all of this information here to come up with something. So the volume is 81. So if I were you, I would do volume equals. A cuboid has, I'll just read this quite carefully. So that's 2x and x. The length of the 12 edges is given by this one here. of the 12 edges. So I'm not immediately seeing anything on that one. The volume, show that the length of the 12 edges is given by this one here. Right, let's have a look. So because we don't have an x or a 2x there, and there's nothing else in the question, they're going to introduce a y. So this is quite difficult because they haven't actually given you the y. So that's a bit tricky. But if you did that, you could do 2x times x is 2x squared. So you could do 2x squared y. Okay, that would be the first thing to do. The length of the 12 edges of the cuboid, well, there's nothing stopping you from actually just adding them all up. Okay, so you know, you've got an x and another x, and then another x and another x, and you've got 2x multiple times, and so on and so on and so on. So you could just add all of these together, and you'll get 12x plus 4y. So a bit interesting, this one, because they don't ask you to use area. They're asking you to sort of add up the lengths, which is a bit different, but it's good practice. Then when we're in this situation here, we can see they want L equals. So for L equals, you're going to use this one up here. Okay, volume is 81, so you're going to use that to get rid of this. Get the y on its own from the first part, and then you're going to substitute it in here. Okay, and y on its own should be 81 over 2x squared, which makes sense, yeah. Even if you struggle with part A, you should still be doing part B. So use calculus to find the minimum value. We differentiate it, and then we set it equal to 0. So we differentiate it at the top, set it equal to 0, and we get x equals 3. Justify that it is a minimum. Well, justify it is a minimum. The minimum value of L. So the minimum value is when x is 3, and then when you put that in, you get 54. Justify that it's a minimum, you need to do the second derivative. So you want to differentiate, where is it? You want to differentiate this one again, and a minimum, remember, is when the second derivative is a positive value. So you differentiate it again, which is this one here, and then actually you don't need to put the number in, but you could put the number in here. Here there's no need because x to the power of 4 is always positive. But if you put a 3 in, you know, that's fine as well. Okay, you'll get a positive number, and a positive number, look, once a conclusion, a positive number means you have identified a minimum. Okay, time for you to have a go. And that is the end of the chapter.